All right, let's talk about something that feels like it should be impossible. We all know the sun is this gigantic gravitational monster, right? So why don't the planets just, fall in? It seems like they should, but for billions of years they haven't. So what's the deal? Let's dive in.
I mean, just look at the numbers. The sun isn't just the biggest thing around, it's basically everything. It accounts for more than 99.8% of all the mass in our entire solar system. Everything else, all the planets, asteroids, comets, we're all just rounding errors. So with a pull that ridiculously powerful, you have to ask, why hasn't it just hoovered everything up?
Yeah, and just to put that into perspective for us here on Earth, the sun is over 300,000 times more massive than our entire planet. That's not just bigger. That's a completely different category of existence. The sun's gravity isn't just strong, it's playing a whole different sport. You'd think that pull would be completely unavoidable, but here we are.
Okay, so the secret isn't that the sun's gravity is weak. Nope. It's as strong as you'd imagine. The real reason is that there's another powerful force in the mix, pulling in the opposite direction. It's all about this perfect, delicate balance, a cosmic tug of war that keeps everything in check. So here are two cosmic heavyweights. On one side, you've got gravity. That's the sun's constant, relentless pull, trying to drag everything straight into its fiery center. But on the other side, you've got inertia. And what's inertia? Well, it's just the tendency for things that are moving to keep moving. It's the planet's momentum trying to fling it in a straight line right past the sun and out into deep space. So, a pull inward and a push to go straight. How does that create a stable orbit? Why don't the planets just crash or fly away? Well, we have Isaac Newton to thank for a really brilliant thought experiment that makes this whole thing click. And it all starts with a cannon on a really, really tall mountain. Okay, picture this. You're on top of this giant mountain, way above the atmosphere, and you have a cannon. First, you fire it with a little bit of power. The cannonball flies for a bit, then gravity wins and it falls back to Earth. Simple enough. Now you add more gunpowder. Boom! It goes way farther this time, but still, eventually it lands. But what if you could fire it at the exact perfect speed? What happens then? Well, it starts to fall, but it's moving forward so fast that as it falls, the Earth's surface curves away from it at the exact same rate. It's literally falling, but it never gets any closer to the ground. It just keeps going. And that, right there, that's what an orbit is.
So, let's just let that sink in. An orbit isn't about escaping gravity. It's not about floating. An orbit is a state of constantly falling. You are falling towards something, but you just happen to be moving sideways so incredibly fast that you always, continuously miss it. It's a controlled fall that never ends.
And this quote just nails it perfectly. Think about it. At this very second, the Earth and every other planet are falling directly toward the sun. But because of that sideways motion we talked about, they just keep missing. It's this beautiful, perpetual near miss.
So how fast is fast enough? For us, here on Earth, our keep missing the sun's speed is a blistering 29.78 kilometers per second. That's almost 30 kilometers every time your heart beats. It's over 100,000 kilometers an hour. That is the mind-boggling speed we need to maintain that perfect balance, to fall forever without ever hitting our target.
All right, so this brings up a pretty chilling question. If that sideways speed is the only thing keeping us from falling in, what would happen if, hypothetically, the Earth just stopped? Like hitting a cosmic brake?
Well, the answer is, it wouldn't be pretty. Without that forward inertia, gravity would win the tug of war, instantly. There'd be nothing to counteract it, and our planet would begin a one-way trip straight into the sun. The whole journey would only take about 65 days. That's it. That's how crucial that sideways motion really is.
Okay, so we understand the physics now, but that just leads to a bigger, more profound question, right? How did our solar system get so perfectly balanced in the first place? It seems way too precise to just be a cosmic accident.
Well, the answer isn't really luck. It's more like a cosmic version of survivorship bias. Think about the early solar system. It was an absolute chaotic mess of rocks and gas flying everywhere. And in that chaos, there were basically three kinds of objects. The ones that were moving too slow? Yep, they got sucked into the sun billions of years ago, gone. The ones that were moving too fast? They got flung out into interstellar space, never to be seen again. So who's left? Only the ones that had the just right speed to achieve a stable balance. We see a perfect system today because it's made up of all the survivors.
And what's amazing is that this cosmic dance can just keep going. Why? Because space is an incredible vacuum. There's no air, no friction, nothing to slow the planets down. So once an object achieves that perfect orbital speed, there's nothing to stop it. It just keeps on going, maintaining that balance for billions and billions of years.
So in the end, an orbit isn't just a path. It's a testament to a perfect balance, carved out of chaos billions of years ago. It's the result of falling towards the sun and missing, over and over again, in a dance that continues only because there's nothing out there to stop it. It makes you think, if this perfect balance is what keeps us safe, what would it actually take to knock us off course?